Gauss law states that total flux of the electric field over a closed surface is equal to 1 by epsilon 0 times the net charge. So that is the statement of the Gauss law. Today we will see applications of Gauss law. Electric field due to a infinitely long charged wire. Here there is a infinitely long charged wire is there. So you have to find out the electric field at a point P, which is at a distance r from the wire. Here charge density is lambda, charge per unit length. Lambda is the charge density. So total charge on the Q divided by L. So it's called charge density. Then to find the electric field at this point due to this wire, you consider two charge elements here and here. This is A1 and A2. This is the point where we have to find out the electric field intensity. Electric field here due to this charge element is acting along this direction. Electric field here because of this is acting along this direction. Resultant of these two will be acting that side. Similarly, you consider a point here at the same distance. So field here because of this charge element is acting along this direction. Field here because of this charge element is acting along this direction. So resultant of these two is acting along this direction. So resultant electric field at the point is radially acting outward. So field at P, Q, R, S all are equal, magnitude equal, and it is acting radially outward. Field here will be acting that side, field here will be acting this side, field here will be acting that side, and the field here will be acting this side. So it is acting radially outward. So there is a cylindrical symmetry. So here we have to consider cylindrical Gaussian surface of radius r and length L. So Gaussian surface is cylindrical. So we have to consider a cylindrical Gaussian surface of radius r and length L. In the case of infinitely long charged wire, there is a cylindrical symmetry. So we considered a cylindrical Gaussian surface. So total flux is the integral of E vector dot dA vector. Then the circle shows integration is to be done over the closed surface. Now this integral can be written as the sum of three integrals. So here top, bottom, then curved surface. So here curved surface, integral of E vector dot dA vector. Then this is top surface and this is bottom surface. Here you consider a small area. Then intensity is directed away from the wire. So it is that side, radially outward. So intensity here is that side. Then this is the area vector or a unit normal. So here you can see that intensity and area vector, they are parallel. That means theta is 0 degree. Theta is 0. So this term will become E into dA. E vector dot dA is EdA cos theta, but here theta is 0. So cos 0 is 1. So E into dA. Here and here you can see electric field intensity is acting along this direction, radially outward, and this is the area vector or n cap is acting in this direction. So 90 degree angle between intensity of the electric field and area vector or unit normal vector is 90 degree. So this term will be 0. This is E vector dot dA vector is EdA cos theta, now 90 degrees, so cos 90 is 0. Similarly here also intensity that side, unit normal is in the downward direction, so this angle is 90 degrees. So these two terms will be 0. The first term E into dA. according to Gauss law, total flux is equal to 1 by epsilon 0 times the net charge enclosed. Now E can be taken outside, then integral of dA is equal to Q divided by epsilon 0. Then E integral of dA is a curved surface. So curved surface. So in this area of the curved surface is 2 pi RL. This curved surface area is 2 pi RL. Then total charge can be written as lambda into L, where lambda is the linear charge density, charge per unit length. So we have considered L meter of the wire or a Gaussian surface, cylindrical. We have considered a cylinder of length L. So charge on this wire is written as lambda into L. Q can be written as lambda into L. L will get cancelled, and then this, after rearrangement, you will get E is equal to lambda divided by 2 pi epsilon 0 R. Electric field intensity is a vector quantity. So in vector form you can write like this. This R cap is showing the direction of the electric field. Electric field is directed radially outward. So this R cap is a unit vector acting radially outward. So this is a vector form. E vector is equal to 1 by 2 pi epsilon 0 lambda by R cap. Electric field is depending on 1 by R.